In this question, we are given a function f from w to w, where w is the set of whole numbers and the function is defined as fn equals to n minus 1 when n is odd and fn is equals to n plus 1 when n is even, and we have to show that f is invertible, and we also have to find inverse of f. So our fn is given as n minus 1 if n is odd and fn is n plus 1 when n is even. So to show that f is invertible, we need to show that fn is both 1 1 and on 2, and to show that fn is 1 1, we need to show that if fn1 is equals to fn2, then this implies that n1 is equals to n2. Now because our function definition is different when n is odd and when n is even, we will have to consider the cases when both n1 and n2 are odd, or when both n1 and n2 are even, and third one when one of them is even and another one is odd. So let's first consider the case when both are odd. So when both n1 and n2 are odd, we'll have to use fn equals to n minus 1. So fn1 equals to fn2 will imply n1 minus 1 equals to n2 minus 1, and this will imply n1 equals to n2. So fn1 equals to fn2 implies n1 equals to n2 when both n1 and n2 are odd. Next, we'll have to consider when both n1 and n2 are even. So in this case, fn1 equals to fn2 will imply, because both n1 and n2 are even, we'll have to use this definition of the function which is applicable when n is even. So that is n1 plus 1 equals to n2 plus 1. This implies n1 equals to n2. So this is also proved. And third case is when one of them is odd and another one is even. So say n1 is odd and n2 is even, and in this case fn1 equals to fn2 will imply, for fn1 we will have to use the definition when n is odd, and for fn2 when n is even. So this will imply n1 minus 1 is equals to n2 plus 1, and this gives me n1 equals to n2 plus 2. So this shows that the difference between n1 and n2 is 2, and whenever the difference between two whole numbers is 2, they both have to be either even or odd, which is a contradiction because we have assumed that one of them is odd and another one is even. So it is a contradiction. So our assumption cannot be true, that is fn1 cannot be equals to fn2. So when n1 is odd and n2 is even, this statement is not possible. So only two cases are possible, that is both n1 and n2 are odd or both n1 and n2 are even, and in both cases we have shown that fn1 equals to fn2 implies n1 equals to n2. So this shows that our function fn is 1 1. Next we have to show that our function is onto, and before I show that, let's see one thing here. When n is odd, fn is n minus 1, so fn will be 1 less than n. This implies that fn will be even. Similarly, when n is even, fn is n plus 1, that is one number more than n. So in this case fn will be odd. So now to show that fn n is onto, we have to show that every m in our codomain has a pre-image. Now, because we have different function definitions when n is even or odd, here we'll have to consider two cases, that is when m is even and when m is odd. So let's consider first case when m is odd. So when m is odd, we have to solve f n equals to m for n. Now because m is odd and m equals to fn, fn will also be odd, and when fn is odd, n is even, and we'll have to use this definition of the function, that is n plus 1. So here I will have fn equals to n plus 1 equals to m. So this gives me n equals to m minus 1. So m minus 1 is the pre-image of m when m is odd. And because m is odd, the values of m will be 1, 3, 5, 7 and so on, and values of m minus 1 will be 0, 2, 4, 6 and so on, and all of them belong to our domain, which is set of whole numbers. Similarly, when m is even, to solve fn equals to m, I will have to consider the case when fn is even, and when fn is even, n is odd. So I'll have to use this definition of the function, that is n minus 1. So here I get implies n minus 1 equals to m. So this gives me n equals to m plus 1. And because m is even, the values of m will be 0, 2, 4, 6 and so on, and values of m plus 1 will be 1, 3, 5, 7 and so on, and all of these belong to our domain, which is set of whole numbers. So the pre-image of m will be m plus 1 when m is even. So we have found the pre-image of any m in W. That means our function f is onto. So we have shown that fn is both 1, 1 and onto, and that will imply that fn is invertible. And we also have to find the inverse of fn. In fact, we have already done that, that is m minus 1 and m plus 1 when m is odd and m is even respectively. So f inverse m will be m minus 1 when m is odd and m plus 1 when m is even. This is the inverse of f.